So, hello everyone. We can start. Welcome to another Networking Friday. My name is Inês Magosteiro. I'm going to be your host for today's session. I work in Plus Atlantic CoLAB in the stakeholder engagement and consultancy team. And I've been mainly focusing on developing stakeholder engagement strategies and user consultation and participatory methodologies in several European projects. But enough of me. Let's talk about the theme of this session. Today's session will present demonstrators of services that are being developed for the Constellation of the Atlantic by Plus Atlantic under the new Space Portugal project. Plus Atlantic will present here the Atlantic Sense, a geospatial tool for climate resilience and environmental monitoring, and in particular two services that are being developed in this platform. So we will have two presentations, and then at the end a Q&A session. Where you can put your comments and questions to the presenters. Just another note before we start, I'm going to share in the chat a link to a survey that was built for collecting some information about the user their requirements, your requirements about data platforms and services for the Earth observation, and this information can be very useful for evolving the services that are being developed under the new Space Portugal project. So, without further ado, I will pass the floor to Ana Oliveira, that will be presenting one of the modules, the extreme temperatures module. Ana Oliveira is CTO at Plus Atlantic CoLAB and an expert in Earth observation applications, focusing on machine learning solutions for climate risk mapping and impact. So Ana, whenever you're ready, you can start your presentation. Thank you.
Thank you, Inês. Hope you can hear me well. Yeah. Thank you to Air Center to receiving us in this Networking Friday. It is a pleasure to work with you on WP5 of the New Space Agenda. And before going further into the presentation, I would like to express our gratitude on Plus Atlantic side for being part of the New Space Portugal agenda, which is one of the most ambitious agendas that have been put forth during the PRR. And again, thank you to all the participants for taking the time to follow up on our journey so far. So without further ado, I will start by sharing my screen. 1 second. So hopefully you can see my screen now. Yeah.
Yes.
So I will be talking today a bit about Atlantic Sense. Atlantic Sense is one of the biggest and most ambitious endeavor that we have had so far at Plus Atlantic. It has an encompassing view in terms of the expertise that we have in-house, but also looking ahead into the future and to the ecosystem in which we work to try to serve the community at large and the societal needs related to climate change, environmental monitoring, and to offer solutions to things that we think are bottleneck currently in this space. So before going to that, because I figure that some of the attendees might not know what Plus Atlantic is, I will just briefly speak about the entity, what we are, what we do, and what we are. So the CoLAB Plus Atlantic is a not-for-profit private institution. It has the objective to transfer knowledge and technology between the academia and society to boost innovation and also to identify blue economy challenges. In the scope of the Plus Atlantic mission in itself, we have 13 associates. This covers academia, industry, private and public institutions with and without profit. And in terms of topics, we were approved to cover topics related to climate change, Earth observation, renewable energies, and blue economy and ocean. So this is the space in which we act in terms of teams, and this is the representatives of our associates that you can find more information on our website, of course. We were built since 2020, and since then we have had a very steep curve in terms of partnerships and relationship with external entities. Here we have some logo that we have much more. I would like to highlight our international partnerships with the several Copernicus services, from the Copernicus Marine Monitoring to Climate Change and Atmospheric Service, but also with the entities behind, so Mercator, ECMWF, and also a lot of services with ESA, and in addition to that, Horizon Europe programs. So in terms of our lines of activity, as I said earlier, we cover topics related to climate change and also blue economy. And we have three main lines of activity. These development lines cover aquaculture and fisheries with a focus on industrial needs and digitalization. Central line already talked about by Inês, covering blue economy consultancy, and this goes from science literacy to user engagement and consultation, and to support to entities who want to translate science information into practical actionable items. And then for today, we will briefly talk about our geospatial information solution. We call it Atlantic Sense, and it covers several modules. Today we are going to speak only about this one. You can find more information on our website about the others, or don't hesitate to reach out. In terms of Atlantic Sense, it has 4 modules. Today we will briefly speak about 2 of those. So we have oceans and estuaries, coastal hazards, climate and territorial inland hazards, and also we have the platform by itself as a software solution which can assimilate several types of data sets from several institutions beyond our own. So about Atlantic Sense in itself. Atlantic Sense has been promoted as a multi-hazard tool in the sense that is multidisciplinary. We covered geospatial information related to climate and environment from an Earth system perspective. This means that we don't focus only on a single domain, but rather on the several domains that compose the Earth system, from the atmosphere to the ocean, coastal interfaces, also land-based extremes. And we have a very strong focus on extremes. Extremes is one of our keywords in the sense that we do the last mile between what is offered openly by the international efforts such as the Copernicus services and the actual applications on given sites. The need for this last mile application is a matter of special resolution level of detail, especially during most extreme circumstances, because we know that by design, global models and very large-scale models tend to underestimate these effects during the extremes in the local aspect. So why does this make sense to us? So I'm wondering from the audience if you have ever considered the degree of exposure that you have to multiple hazards on your daily life, or also thinking about long-term hazard exposure. For example, do you know exactly what's the footprint of hazards in terms of climate change for the place where you live? Do you understand whether your house is subject to extreme events or not, such as sea level rise, but also others? Or do you consider air quality during your day-to-day life, if you're taking kids to school or if you're going biking to work? We argue that most of this information is very specialized and common citizens struggle to get access to their own environmental footprint, their own climate hazard footprint, and this is something that we are trying to solve. So there are 3 main drivers for this. One is the fact that climate change induced changes in our hazard profiles, in our natural hazards profile, is very localized. So we know that the triggers for climate change are global. The challenge is global, but the effects themselves are usually felt at the local level. In our cities, in our beaches, in the places where we live. And this means that we have to translate these very background conditions into very localized impacts And we have to go from the danger itself, the hazard, towards the impact. So what's the outcome of these hazards? How probable are they? How severe they are? And what's the expected outcome? There's also another issue which fortunately was now approved with COP30 in Brazil, Belém, which is about the specialization and silos. We live in an era in which the scientific development has been very, let's say, optimized per technologies and per degrees of expertise, but then experts tend not to talk to each other. So there is a missing opportunity to overlay different hazards which come from different backgrounds, different areas of science, to talk to each other and to establish what is called the multi-hazard framework. And this is meaningful not only in terms of climate adaptation, but also in terms of early warning systems and how to act. Because plenty of times we have hazards that are overlapping with each other, sometimes in space in time, and sometimes they even lead to what is called cascading effects, which is when one hazard leads to the other. Then we have another problem, which is about transparency, participation, and this ties with the question that I made earlier about common citizens from outside academia don't having a strong idea on what's their risk profile or what's their exposure profile. So this information is so specialized today that is difficult for a common citizen to apprehend fully the scope of exposure that they have, either in terms of infrastructure or in terms of health. So at Plus Atlantic, we try to translate this. This is basically our main challenge. And this is the basic assumption that we want to respond with Atlantic Sense. So I will briefly go through some examples. Pedro is going to focus on this one. One of the reasons why it doesn't make sense to us is to map, for example, what's the sea level rise exposure in our own coastal infrastructure, and Portugal is a coastal country, so it means a lot to us to understand what is going to be the future, and Pedro will expand on this. Another topic is air quality. We understand that air quality is a function of our own activities, for example, traffic, but also port activities. So we are subject to air pollutants, which we do not control in terms of emissions. And what can we do about it? And how can we improve our city's design, or at least our day-to-day activities, to minimize the degree of exposure to these harmful substances? Other examples are related to ecosystems health and ecosystem services. So more and more we talk about nature-based solutions and how these should be valued in objective and subjective terms, of course, tangible but also intangible services that the nature provides. And we can offer solutions that can be integrated with the other hazards to see what's the benefit of adopting an ecosystem services approach. So these are just simple examples which you can see in the platform. But for today, I'm going to focus on the human health impact in itself to showcase one of the use cases that we have been developing under WP5 and WP4 of the new space agenda. In terms of health, we know that heat waves are becoming stronger, more severe, and we know that in the European countries, especially in those that are in Southern Europe, these heat waves are not only becoming more severe, but the population is also become more elderly. So this means that we have a compounding effect on what is the hazard becoming more extreme and the population becoming more sensitive. This means that in the end, we should have, by principle, by design, stronger impacts, stronger outcomes. We also have to acknowledge that we have been subject in the 80s to very strong pressures for urbanization, uncontrolled urbanization. So most of our cities are gray by design, which means that they do not encompass the so-called nature-based solutions that I talked earlier, and they are not ready for these hazards that are coming. I will be talk about heat, which has a strong influence from the urban design and the urban planning. And Pedro will also expand a bit on the interface in the coastal setting. So this means that in terms of weather forecasts and climate projections, for that matter, tend to be something supplied by national weather services or international institutions, like ECMWF. They are very precise nowadays, despite what some people may advocate publicly. The fact is that the degree of accuracy of these background predictions is really, really great, considering that we are talking about chaotic phenomenon that is three-dimensional and also has the time component, so we can talk about 4 dimensions. The problem or the caveat is that these national and international institutes, because their mission is to cover the country scale or the regional scale of multiple countries, they don't go to the level of detail of the neighborhood or the street or the city. And this means that by design, if we know that the cities affect the lower atmosphere, there is a missing opportunity in terms of considering what's to these background forecasts that are precise in the background, but lack sufficient detail within the cities. And this is important because, for example, if we look at Portugal as an example, we can see that heat waves have been increasing the most in the coastal setting. And this does not mean that the temperatures are higher in the coastal setting. This just means that the temperatures are moving faster, are warming faster in the coastal setting. One hypothesis for this is that the ocean is also warming faster. So there is like a mismatch between the coastal proximity and the inland areas. But when we look at impacts, and now I'm showing the incidence risk ratio for hospital admissions in Portugal, we see that we have a very patchy pattern. And this is because the impacts themselves, so the excess hospital admissions and the disease burden that this entails, so the cost that this entails for the public health sector, is a function not only of the hazard pattern, but also of the social economic aspects, what facilities they do have at a given municipality, and all of this sums up and interacts with each other, these predictors, to come to a certain impact, a certain degree of loss, being economic loss or lives loss. But what if we look behind this to specific heat waves? We can have a look, for example, to the heat wave of 2003, which is very famous, and we can see that the picture from before is actually not corresponding to the picture of a specific event. And I'm bringing this to tell you that even though we could do an analysis like the one before to show what's the typical risk profile, if we look at the weather scale on a day-by-day basis, things change. And for example, if we go to the 2003 heat wave to the 2016, we can see that the pattern changes, the metrics changes, and the excess hospital admissions amount and locations where it reaches maximum also change. The same happens to temperatures. So no heat wave is alike the other. And if we go even more recently to 2017, we see even more aggravated impacts and more aggravated temperatures, which ties really well with climate change prospects that we know are happening. So how can we zoom in even a bit further? We nowadays have plenty of observations, remote observations, in situ observations from citizen-owned stations. We do have very good background forecasts, especially in Portugal with AROM, which is the model set up by IPMA. And we actually have a deficit in terms of in situ stations by which you can do statistical or machine learning downscaling. But then we can use these stations that I'm showing now, these are NetAtmos stations from citizens, and we can pinpoint which of those are actually quality enough to model something from those that do not. For example, here you can see that approximately 50% of the stations are useful, while the other 50% are actually not useful in terms of accuracy. And with this and the background forecasts, which you are seeing here, we can go from something like this. This is an AROM forecast for Lisbon in a given heat wave, and you can see that there is no meaningful landscape pattern for the city of Lisbon. So I'm talking about the green spaces within the city. But when we employ machine learning techniques, we can start to see actually what is the cooling benefit of certain green areas compared to their boundaries, for example, Monsanto, and at the same time, we can also see the gradient, the temperature gradient from the background conditions coming from our home. So we have the best of both worlds, and it's trained on in situ stations, which means that it's more adequate in terms of the degree of exposure at the city center compared to background conditions. And we can then make a statement that people who are in these most exposed neighborhoods will likely have an exposure that is 1, 2, 3 degrees higher than what would be expected by the background weather forecasts. So with these kinds of tools, we can go beyond and offer climate projections. And by climate projections, we can combine with land cover changes, and actually we start having a digital twin, which is what we want to offer, something that goes beyond forecasts and historical scenarios, and also goes into, to historical and next day forecasts, and goes into scenarios. So something that we can change land use, land cover. And here you are seeing an example from Lisbon, in which we changed the land cover to reflect the current regulation. And you can see what's the relative impact of that land cover change in terms of new spots of cold and new spots of heat, as long as these new areas are developed according to the plan of the PDM, the local regulation for urban planning. I don't know how I am in terms of time, if I still have some minutes for a demonstration, Ines. Can I go on?
Yes, Hannah.
Yeah?
Please.
Okay. So in terms of Atlantic sense, I think the first thing that we have to have in mind is that natural hazards and their corresponding risk have 3 temporal scales. We don't know what's going to happen in the future. There is a road ahead, and multiple scenarios from a climate perspective are possible. But we know more or less what we have in the present. Sometimes we forget a bit about the past because it's long gone. We don't feel it anymore, but actually is very meaningful for us to have consistent temporal observations and temporal mapping of extremes so that we can somehow extrapolate how they can become in the future different, let's say, outcomes. So this is our choices in the end. So in Plus Atlantic, what we tend to do, our way of working, is that we have very backward looking in terms of establishing relationships. Historical observations are typically the playground for us to build models. They can be physical models, they can be deterministic or data-driven models, but the past and observations is the ground truths with which we train whatever we do. And with these past models very well documented and validated, we can then start to implement in 2 scales, weather forecasts for tomorrow, so acute risks, and climate projections even further beyond into the future. So what are the alternative scenarios? And I'm going now to give you 2 examples, one of past model development, which will then become something for the future, and next day forecasts. In terms of yesterday, so in 2018, on the 5th of August, there were a lot of news coming around because it was a very strong heat wave. And actually, we had approximately 500 people in Portugal dying in a single day, which is double or more than double what should be expected during the summer. For comparison, this is more or less the same amount, the same magnitude of excess mortality during a coronavirus day. So this is to say that heat waves matter, they have an impact, this impact can be measured. And this is just a single day, so it's not the full heat wave. So now I'm going to present to you, and I invite you to go to Atlantic Sense. I invite you to scan the QR code that you have here. There are other ways to reach the platform. You can either type the address or you can search on Google because it's already indexed. And if you enter the platform, you can see the basic information in the menu, and you can also go to the right-hand side to the top to scroll down to further information about the platform and what it contains. I will make a slide stop here. Okay, assuming that you have scanned already, I now invite you to go to this specific event that I just talked to you about. So you can do this by selecting the team and the area. Of course, you can go directly to the layer, but that is more difficult. So you can go to the theme, the area of interest, and it also select during the calendar to the 1st of August of 2018, which is the time of interest for this event. And you can see the video that I'm showing depicting how to do that. Okay. Assuming that you already did this, you can now select the daily maximum temperature per municipality, which you will see in the menu of the layers. And if you pick a given municipality, in this video I picked Lisbon just as an example, you can see actually the temperatures, how they increase in time, and you can hover over the plot to see which day was the warmest. And this is just the absolute temperatures. I'm not going to show all the layers, but you can have the deviation, so the excessive factor for this, and you can also have a look at the minimum and other parameters. Now, one thing interesting about temperature during the summer is that any impact that you measure from it has to be accounted for in terms of ozone. Ozone goes hand in hand with temperatures. So here I'm going to suggest you to hide the air temperature layer, and you can do that without omitting it just by clicking on the eye icon that you have on the active layers menu, and you can turn on the daily ozone exceedances per municipality or the daily ozone. You can actually select one of both. The daily ozone represents the absolute concentrations per municipality, and the exceedances is the deviation from the health impact threshold that one should account for. So in the video, you can see an example from the absolute ozone. And you can have a look and see how it increases along time, just like you did for air temperature, to find out that the day is actually the same if you click on Lisbon. But now let's go to the compound effect of these two. Oh, sorry. So I invite you to select a further layer, the daily excess mortality per municipality. This is computed having into consideration the other variables, in this case, during extremes during the summer. And if you pick the municipality of Lisbon again, this should be working and it's not. Yeah, no, it's working. You will see the pattern of the excess mortality, and you can actually pick a given municipality. And I'm going to pick Lisbon again, just to be coherent with the previous slides. And you can see the excess amount of mortality. And one thing that you can see is that the the peak of excess mortality is actually 1 day later. And this is usually the case. So peak mortality tends to be 1-2 days after the peak of temperatures and the peak of ozone, because there is a lagged effect that tends to be between 24 and 48 hours. There is much more to be said on this because these are aggregated numbers. But if we start to peel down the onion to see per age group, per gender, by chronic diseases, there is a huge amount of information that you come to. And it's even interesting to say and to see that the proportion of ozone impact and temperature impact is also varying across the age groups and across the major diagnostic groups. So it's not the same for the whole population. But these are just preliminary results that you can see online, and you can play around with the layers.
And sorry.
Yeah.
No, 1 minute just to finish, okay? If you can.
Okay. Thank you, Ines. So I did have another example on marine heat waves, but not to take time from Pedro, I will suggest that you go through the platform afterwards, of course, because you should be attentive to our presentations now. Scan the code, leave the address in your favorites, and have a look also to marine heat waves forecasts. And with this, I will jump to my last slide, which is just to make a very strong thank you to the full team of Plus Atlantic. What I've shown you today is by no means a small effort. It entails contributions from all of this team, this multidisciplinary team, from people doing machine learning to people doing integration, from people doing UX, UI, development, even taking care of the machines. So this is really a group effort, and I would like to make my thank you and show the appreciation for the team supporting this effort. And now I pass the word to you, Pedro. Thank you.
Thank you, Anna. Just before Pedro starts, I would like to remember you that I put the link in the chat for the feedback survey, and so please, if you can answer this survey, that would be very useful for this project. So now, Pedro, you can start. Pedro is a senior scientist, oceanographer with expertise in coastal processes that is leading the coastal hazards and risk team at Plus Atlantic. Whenever you're ready, Pedro. Thank you. 20 minutes to present. Okay.
Thank you, Ines. So good afternoon to everyone who is attending. Thank you for this opportunity also to present the services that we are developing at Plus Atlantic that are being integrated in Atlantic Sense, and they are related to coastal hazards services. So to give you a little bit of context, in Portugal, the low-lying sandy coast is 50% of that coastline is under erosion. And since 1958, we're already lost about 1,380 hectares of territory due to coastal erosion. And for that reason, the environmental agency has been very active in promoting interventions in order to protect the coast, such as sandy nourishment interventions or even art structures to protect the infrastructure and also the urban areas in the coast. And in the last 15 years, just to have an idea, we have invested about 350 million euros on this type of protections. Along the coast, the environmental agency also has done a very good job on identifying the hotspots of erosion, which are the critical points where the lack of sand essentially is causing structural erosion. So basically, these sectors are losing, the shoreline is retreating constantly. And in these areas they are also identified because they have a very high exposure of urban areas and infrastructure. The natural environment, such as dunes, don't have the capacity to attenuate the erosion process, so they have lack of sediments as well. And for that reason, these areas are constantly exposed to coastal overwash, so basically wave impact during the winter. Under climate changes, including sea level rise and storminess, we expect to see these scenarios getting worse, so erosion will potentially intensify. Potentially, we will also have new hotspots of erosion along the coast that have not been identified yet. And the interventions are it's a process that will continue over time and is potentially expected to increase. As well, the extreme events are potentially also becoming more common. And for that reason, these sites required a number of services, a number of information, including monitoring environmental variables, perform risk assessment, and also in early warning tools to support rapid response mitigation actions. So at Plus Atlantic, we use a number of tools and methods, including a variety of observations that come from different sources, such as in situ, remote sensing, local remote sensing, or satellite remote sensing observations, as well combined with numerical models, process-based models, or statistical models, together with geospatial tools and analysis to be able to respond to different or develop different applications. And as I mentioned before, the applications are focused on these three elements. So monitoring essential variables that describe the evolution of the coast and also support the analysis of risk assessment, as well provide information, short time information in order to be able to provide a response to coastal decision makers. So all of this is integrated or is part of the integration in the Atlantic sense. So starting to talk a little bit about the coastal erosion of hazards and the monitoring and the risk assessment. We use on the most of the data that we use is coming from satellite, and in the last decades, this has become the normal scenario of using satellite information to look at the shoreline evolution. Part of that is because the sensors have increased significantly the spatial resolution, but also the fact that they have an ideal spatial and temporal coverage because they constantly collect data with regular revisit times all over the globe. And part of this data is still freely available, so it's also very important. There are a number of methods to identify the key indicator, the shoreline position, to look at coastal erosion. We have worked with several methods, part of developing of some of them. And now we are using, for example, the CoastSat Python code to identify the shoreline position in satellite imageries coming from Sentinel-2 and Landsat. Essentially, the shoreline position using the satellite imagery is defined as the waterline, the instantaneous waterline that is detected on images that are collected at the time the satellite is passing over the coast. And there are many different approaches to classify the image that we collect from optical sensors. And then also there are plenty methods to identify the edge between land and water, as the CoastSat is one of them that provides very good accuracy. With the collection of this information, we start to create time series of shoreline positions, as you can see on this left image, that enable us to understand the evolution of the coast. There are many ways to analyze this data, but one that is typical is to select specific transects, which are these cross-shore lines that cut or intersect all the shoreline positions. And from that information, from the intersection of these transects with the shoreline positions, we get what we see on the right, which is a time series of shoreline evolution along a specific section of the coast. And from that, we can understand if the shoreline is moving towards the sea or towards the coast, as well calculate the velocity how this shoreline is moving, and from that identify the trend, which is the traditional element used then to evaluate the future evolution of that specific section of the coast. So now I'm going to show one product that we developed recently and added to the Atlantic Sense platform, which is the mapping of the shoreline evolution and trend along the entire Portuguese mainland coast. I have to now, you can access the Atlantic platform. I think you already know the link, but now I have to get out the presentation mode and show you the small video that I prepared to guide you along this demonstration. So when you are in Atlantic Sense, you select the layer coastal, and then you will have a number of options, and you select coastal geomorphology and shoreline trend. And now you see the different dots that they are classified according with these classes. So and each of these dots is related to the linear trend, as I explained it before. And in addition to that, you can also look at the time series on each of these transects. So you can, by selecting any of these dots, another window will open on the side and will provide you the time series, the linear regression rate of change. As well, you can adjust the window of analysis to different times, different period of times that will adjust as well the linear trend that is computed for that specific time. You can also download this data and do your own analysis. So you are free to explore other statistical methods to analyze the data, to analyze specific periods of time, as it is possible to download a CSV file, which is very simple to read by any type of software. So this is just the initial video to show you how the data looks like. And now I have some demonstrations as well, how this data can describe the recent evolution of the shoreline along the Portuguese coast and how that compares with what the environmental agency is also mapping. Starting with this, just a couple of hotspots of erosion. And this is a report from the environmental agency where you can see that in the recent years, one of the main hotspots in Portugal with the highest rates of erosion is located in the north of Portugal. It's this section between Cortegaça and Furadouro. You can also see, and this is the one advantage of collecting this continuously along the space, is that these shoreline trends are not homogeneous along this section of the coast. There are some areas that are more that have more intensified erosion than others, and we can also analyze that from an Atlantic sense. So if I open now this video, I will show you this specific section, and we can just click on different sections along this sector. We can identify that, for example, in this southern part, the rate of change is minus 3.55 meters per year, so lower than the what was provided by the environmental agency. So indicating that in this hotspot sector, the southern part is not the most problematic. As well, you can see that this northern section is the one with the most intensified erosion process, with rates of changes getting up to 7 meters per year. I also have a GIF that demonstrates. It's not in this one. Okay. In fact, this is a GIF showing that specific section. As you can see, this is the north part where the erosion is more intense, and you see how fast this car park just disappeared. Another place is located, and this is one of the hotspots with showing the most intense erosion process in the recent years, is located in the coast between Covagala and Lavos in Figueira da Foz. And also I have here a small demonstration of the results for this section. What is interesting in this section, this erosion problems on the southern part is due to an extension of a jetty in the north part, which also created positive trends in the north. So very high positive trends which means the sand is accumulating the northern part, and that sand is not coming to the south, and then creating this erosion process. And now I'm zooming into a specific time period where just the construction of the jetty just finalized. So you can exactly identify the moment with this time series where the impact of this intervention affected the shoreline evolution, as well quantify the changes that affected the coastline. So this is the case of Figueira da Foz that I was just showing. So the northern part accreting significantly and the southern part eroding. We are now also trying to fuse the data in order to take the profit of having survey data collected by the environmental agency. At the same time, we collect satellite data, and we are applying correction methods to improve the precision of these shorelines, combining all this information together. So getting slopes from the topographic surveys, getting the water levels from CMEM's forecasts, and all together we can improve the quality of the shoreline detection, which then it provides a much more, let's say, realistic tool to be able to actually monitor these interventions. And this is an example, our time series and the top panel without the corrections that we are applying now compares with the survey, which is this red line. This is the data measured with very high precision sensors. And then when we apply this correction, we can have a very good match between the two data sets. As well, you can see with this type of time series, we can see that the critical distance of erosion, which is the point where basically the beach disappears, can be detected over the time. So this in 2019, when that section of the beach reached the critical point, there was made an intervention. Then there was a period of time where the sand was in equilibrium and the beach profile was resilient. But then more recently, and now this section of the coast is reaching again the same critical erosion distance, and then for that reason is expected another intervention soon. So being able to evaluate how long these interventions last, when do we reach a critical point, can be also monitored by combining survey data with satellite. In addition to that, this information is very important to provide projections of the future evolution of the coasts. So then we can identify where are the areas at risk, potential risk of retreat, which also means we can overlap this information with infrastructures and identify which sections of the coast need more protection. And now I'm going to talk about the early warning component, the short-term information that can be provided by models, but also combined with satellite. We have a system of forecast, of operational forecast, that combines a number of models, and we divided them in tiers. So they are layers of specific models that provide specific information. So in tier 0, we have let's say, the boundary conditions, the models that provide the sea levels and the waves that arrive to the coast using different types of models, the MOHID water for the ocean circulation, and the wave watch tree for the waves. And then when we get to the coast, we have the tier 1, which is a rapid assessment of the potential impact of these conditions on the coastal profiles. So we compare the coastal morphology with the boundary conditions of waves and sea level, and identify which potential of impact we will have, but in a fast mode with the reduced complexity statistical models. But then in very specific locations, and this is something we are still developing, we are calibrating and preparing models, high-resolution models, to be able to respond in more detail and provide in more detail where exactly, for example, overtopping will take place or inundation, and where exactly is the critical point that needs to be protected.
Pedro, sorry to interrupt. Just one more minute, okay, to finish.
Okay.
Thanks.
Okay. So we try to translate in Atlantic Sense the information of these models into simplified information that can easily provide an idea to stakeholders, decision makers, of the potential impact of upcoming storms. So that's why we use this type of translation. And here I have a small demonstration, but I will leave maybe this for the last. Is just to show you how the platform visualize this information. We are also trying to validate these models, because these are very complex process to be able to respond to predict. And so we're trying always, when we have it's very hard to have data sets on the coast to predict this type of process. There are no information about this. So we try to collect qualitative information from the media, also from social media. So this summer we had this airing storm that provided a number of information along the entire Portuguese coast that enable us to qualitatively evaluate our model capacities. And we build this story map also where we explain these comparisons. And now we are as well developing the integration of satellite-derived bathymetry into these high-resolution models, because as the coast changes, not only the shoreline, but also the underwater morphology changes, and then that affects the model predictions. So we are trying to then integrate that information to update the bathymetries of the models and improve the capacity of predicting this process with high-resolution models. And so I'm going to, I think I still have a few seconds, just also to say thank you to the entire team that is being involved. Not, of course, everyone, but partially a large number of these colleagues have been involved in the development of these tools, of these applications, and they are still pushing for other advances. So I'd like to thank everyone, and also advertise for this survey to give us the feedback of these services and applications. That is very important for us. Thank you very much.
Thank you very much, Pedro. So I will open now the Q&A session. Maybe we can stay a bit after 1 p.m., 5 minutes or something if it's needed. We have some questions here. So Nuno Moreira, thank you, Ana and Pedro. A question to Pedro. Could you provide an indication on the algorithm used with satellite data to define the shoreline, including sensors, bands, etc.? Do you want me to repeat?
I think I think I understood. The algorithm, it's the CoSat Python toolkit that is available online. It's a free tool, open access code. And we are using Landsat sensors, Landsat and Sentinel. So basically we are using all the optical imagery from these two sensors. And then we apply, as I show, we apply our own, let's say, algorithms to improve the detections in order to make sure that we don't have tidal influences or even wave influence when we have larger waves that can potentially affect the data. Mostly when in the cases when we are analyzing, let's say, short-term process, not long-term. In the long term, typically this process that I'm explaining, they don't affect so much the data, but in the short term, it's important to include these corrections. So I hope that I answered the question, but if not, just ask me again.
Okay. So I have another question from Montana Mazuz. So coastal hydrodynamics, did you develop scripts for extreme events? I think this one is for you, Pedro, also.
I guess he's mentioning about the forecast. So basically, the forecast is in operational mode. So is predicting the boundary conditions offshore as we simulate the meteorological information that is input in the models. So, and then we define storms, or we define impacts based on the relationship between the water levels predicted at the coast and the beach profile. So the information of the morphology at the coast. So we define specific morphological factors on the coast. So the base of the dune, or the base of the seawall, and the top of the seawall, and the top of the dune, for example. and comparing that water levels, the elevation of the water levels with that indicators, we can define if it's the potential impact is a collision, is overwash or flooding. So it's basically this combination of or connection of information that provide us what is the impact of an extreme event.
Okay, Pedro.
That's
Thank you. Another question for you from Inigo Aguilera. Any clue why the Furadouro area is getting more eroded than the surrounding ones? And is there any action plan in place to prevent or diminish that erosion?
Furadouro, the north of Portugal, Inigo, is has already long-lasting problems of lack of sand, mostly because of the artificialization of rivers in the north, the Douro. And then there are locally some additional problems due to the coastal defenses. So jetties that were built to protect some parts of the coast, but then expose others. So essentially, that's the story of the north region, the north coast of Portugal, and the Furadouro is one of them. I know that APA is taking actions there. He's performing nourishments. I don't know exactly this year if they have done any intervention there, but I know that is one of the hotspots. So is all the hotspots that APA has identified are being let's say subject to interventions. So in order to protect the adjacent coastlines.
Okay, thanks. Any more questions? Questions for Pedro or Ana? Do you have any more questions? Okay. It seems that everyone is very clarified about everything, so no more questions here. I think so. Okay. Another one. Okay. Question for Ana. Sorry, maybe the last one we were going to do. Question for Ana from Beatriz Reis. Would you consider developing a hazard layer for wildfires in Portugal, Ana?
Yeah, I think so. Definitely. Of course, as with the air temperature, we rely in extensive collaboration with the public entities involved. So this would not be only upon us to pursue, especially since wildfires tend to involve many entities, such as also civil protection. But from a physics perspective and from a climatological perspective and from a competences perspective, I figured, yes, we can evolve in that direction. And I can actually share that we do the evaluation and quality control of two fire-related products under the Copernicus climate change function for evaluation and quality control. So we do have some experience with that type of data. But as with the air temperature and other aspects, it's not a standalone challenge that we do alone in-house. We have to rely on partnerships because most of these things benefit from multidisciplinary interchanges with academia, public stakeholders, and we do have the National Collaboration Program ongoing with APA and IBMA, and wildfires, for example, have been one of the topics that we have discussed during a use case. So yeah, hope this was clear.
Thank you so much, Ana. So I think the last one we have here from Montana Mazus for Pedro. Still, is it used for early warning or just erosion, like the tool that you're talking about, Pedro? And how adaptable are they to the local context in North Africa, for example?
Thank you, Montana.
Montaha.
Okay, so well, the early warning, the tools that we are using, it can be used also for erosion and flooding, and so both things, both process. So and the context of North of Africa, it is possible, of course, because we feed the models by using ongoing or existing meteorological models and other forecasts provided, for example, by Copernicus, and these models cover the entire Atlantic, for example, and then we adapt our own models to the locations where we want to provide more detailed forecasts on the coast. And for that reason, is possible to adapt to Africa or to anywhere along the Atlantic or in the globe. So it's a matter of let's say adapting the models locally, and then of course it will be important to have good information such as bathymetries, topography along the coast in order to be able to provide more detailed information along the coast, because these models, as you get closer to the shore, they increase their resolution, and the information that is provided to run them, it's also it needs to be also a high resolution.
I think there is room for one last comment from Montaha. Thank you. And he wants to know if you collaborate with universities or research institutions for pilot projects in emerging regions, and if yes, how can early career coastal engineers participate?
Well, in Plus Atlantic, we collaborate. We are very open to collaborate with any institution anywhere around the Atlantic. Particularly, I had in the past some collaborations with the universities in Africa. And I mean, it's just to get in touch with us. I think that's the most important. Send an email, we can arrange a conversation to discuss potential collaboration.
Okay, thank you. Thank you, everyone. I think we can close now the session. Thank you once again to Ana and Pedro for their presentations. And I think keep posted for any news about the Atlantic Sense in the website and social networks. And yeah, thank you. Thank you, everyone, for participating. And have a nice weekend, everyone. Thank you.
Thank you.